All right, so today we're looking at circles and then area of the shaded region. So first I'm just giving you a picture of a circle. Right here would be the center of my circle right there. So my circle is the set of all points that are equidistant from the center, so equal distance. So that distance is really the radius. So if I picture putting a little push pin here and drawing a string and I make it this long, I could make a perfect circle using that distance of the radius. Okay, in the video, we should have seen that for pi, right, it's the ratio of circumference to diameter. So if we want to get just the circumference, right, I could multiply each side by diameter, and I can express it as pi times the diameter, or 2 times pi times the radius, because 2 radii will equal the diameter. Okay, pi, just so we have a sense of what it is as a decimal approximation, we usually say 3.14, but if I go a few more decimal spots, it would be 159, and then we could keep going because it really never terminates. We know that pi roughly is about 3.14. Okay, area of a circle is pi r squared. We're going to see today that we're also asked to find the area of a sector. So the sector is like a slice of pie. It's a portion of the overall area. I'm going to call it slice of pie here. Okay, and then the segment right here is this shaded region, where really to get to it, we're looking at the sector first. We want that slice of pie, and then take away this triangle right here. So the segment is a sector, but taking away the triangle. Okay, so we're going to start off with a few basic problems, and then we'll get gradually a little bit more complicated. All right, so first up, example 1, find area and circumference. So we're given that the radius here is 8. So we know that area is pi r squared, and circumference is 2 pi r. So if I plug in a radius of 8, right, I have pi times 8 squared, so 64 pi for my area, but units squared. And then for circumference, I have 2 times pi times 8, so 16 pi, and then just units for circumference. Right? And our circumference is essentially just like perimeter. We just don't have edges, right? Circles are not polygons, right? They don't have edges. All right, in the next one, I'm giving you that the diameter is 20. So if the diameter is 20, the radius has to be half of it, has to be 10. So now area is pi r squared, and circumference, I could build off of the diameter or the radius, it doesn't matter. Since I had the diameter first, I'll say pi d. All right, for area, if I plug in the radius of 10, so pi times 10 squared equals 100 pi. Okay, and then here, in my second one here, we see that the diameter is 20, so 20 pi. I'll say pi times 20 first, and then rewrite it as 20 pi. All right, so my area ends up being 100 pi units squared. Okay, and then circumference here is 20 pi, and then units. All right, next up. Here I'm giving you, in example 2 and 3, I'm giving you circumference, and I want you to find the area, and then vice versa for example 3. So I'm giving you one of the two, and I'm asking you to solve for the other. So in the first one, I'm saying, well, circumference is our starting point. We know that the circumference is 16 pi. So I know that circumference is 16 pi, and I know that its formula is 2 pi r. Okay, so when I see that, I go, oh, okay, my radius is 8. So how am I getting there? I can use substitution. If I plug the 2 pi r in for the c right there, I can have this new equation where 2 pi r equals 16 pi. And then from here, I'm just trying to solve for the radius, right? I can already see that it's 8. I'm just trying to confirm it so you guys can all see it too. So now if I divide each side by 2 and by pi, right, it's simply confirming that my radius is 8. Okay, so now I want area. Area is pi times the radius squared, and my radius is 8. So pi times 8 squared, I would get 64 pi, right? We actually already solved that up above in problem 1. All right, so 64 pi units r squared. All right, in example 3, we're just going in the opposite direction. So here we are asked to find the circumference when we are given the area. So area is given as 16 pi units squared, of course, and we know its formula is pi r squared. So again, I can use a little substitution, plop the pi r squared in for the a right there, and say that pi r squared equals 16 pi. And I'm guessing that most of you can see that the radius is 4. I'm just going to show you the mechanics that get us there. So divide each side by pi, radius squared, then equals 16. Solve by taking the square root. Algebraically, I get plus or minus 4, but my radius, it really can't be the negative, so my radius has to be 4 units. So now that I know my radius and I want to get to circumference 2 pi r, I'm just plopping in that 4. So 2 times pi times 4 gets me 8 pi units. All right, next we're getting to a sector problem. So find the area of the sector. So really, again, a sector is just like a slice of pie. So how do I get to that slice of pie? So I'm looking at first, what's the ratio of the sector here, right? Its angle measure to the whole circle. What's that ratio? So I'm going to write this out as the sector angle measure. In this case, we can see that it's 60 to the whole circle, which will be 360. Okay, and then we're going to multiply that by the total area of the circle. Because we're really looking at a portion of the total area when we're looking at our slice of pie. All right, so again, my sector is 90 degrees, right? I see that right angle right here, 90 degrees. So ratio of sector to circle. So 90 to 360, and then my circle area is pi times r squared, so 12 squared. So I'm really looking at, well, what is 1/4 of 144 pi? So what's 1/4 of 144? That's 36. So I get 36 pi units r squared. All right, so again, the whole area would have been 144 pi, but I just need 1/4 of it right there. So 36 pi it is. Okay, next I want the area of the segment. I want this little sliver right there. So that area is always looking at the sector first and then taking out that triangle. So that triangle is actually something that we should notice is equilateral. So what I can see for the triangle is that these two legs here and here, they're both radii, and any radius for a circle has to match the radius anywhere else that we draw it, because it's just connecting a center to a side. So your radii will be congruent. So then if I just know that, then I know that these two measures have to be the same, and what's left over is 120. So I have a 60-degree angle here and here. So I'm going to give it another little tick mark there to show that it's an equilateral triangle. So here I'm looking at sector minus triangle, and I just happen to notice that it is equilateral. Okay, so my sector, I'm looking at the 60 degrees to 360, which will be 1/6, I'll reduce that in a minute, times the area of the total circle, so pi times 4 squared. So I'm taking 1/6 of 16 pi. So if I reduce, let's say I picture that 16 pi over 1. So if I reduce that 16 and 6, they're both divisible by 2. Here, that would be like 8 and 3, just like that. So I have 8 pi over 3 units squared would be the sector, and then I have to take out that triangle. So my triangle, let me just draw it out like this. Again, it's equilateral. So I know that I could split it right down the middle and make two 30, 60, 90s. So I have a 60-degree measure here, 30 here, here, and another 60 right here. So each side is 4. So I know, again, here this is 4, which then gets me 2 and 2. And then that height, let me use a different color to make sure it's clear. That height would be the 2√3. Now it's equilateral, so I could do 1/2 apothem times perimeter, but if I know a side, I usually just split it down the middle, so I can do 1/2 base times height. So area is 1/2 base times height. So 1/2 of 4 times 2√3. So 1/2 of 4 is 2 times 2, we're back to 4. So 4√3. So I have this part and I have this part, and I have to subtract them. So I have 8 pi over 3, and then take away 4√3, and then leave your answer as units squared. Okay, next part. All right, so second page here, we're really looking at shaded region problems, where we're trying to get to the shaded region, and that's really what we were doing with this sector and this segment anyways, so this is just a natural extension. And they kind of gradually get a little harder. The ones at the top of the page are pretty easy, get a little harder as we get into D through F. All right, so here looking at the first one. So here I'm saying find the area of the shaded region. Figures are rectangles, circles, semicircles, right triangles, and regular hexagons. So we can assume that, even though we haven't marked all of the tick marks that we're used to seeing. So we know what these shapes are going to be. So when I look at A, I can say, okay, well, this is a rectangle with 6 circles that are being removed. So if I make a little plan down here, I can say, okay, well, I've got to find the area of the rectangle and then take away those 6 circles. All right, what information do we have? Well, we have that this whole side here is 10. So then that tells me that since there's 2 circles here, that my diameter would be 5, which means that a radius would be half of that, 2.5. Okay, so rectangle, here I know that this side is 10, right? That's 2 circles. This one is 3 circles, so 3 diameters. This side must be 15. All right, so rectangle, we know our area is base times height. So 15 times 10, we have 150. So there's our rectangle. All right, for our circle, we note that the area is pi r squared, but we're going to have to multiply by 6 in just a moment. So one circle, if I plug in a radius of 2.5, pi times 2.5 squared, right? And then I'm going to multiply that by 6. So I have 6 circles, 6 times 2.5 squared. That's going to get me 37.5. And then pi right there. So I need to subtract the 2. They're not like terms. This one does not have a pi, so I leave it as is. I have 150, that's my rectangle, but subtract away 37.5 pi. And then units are squared. All right, moving on to the next one. Here I see that I have a circle with a triangle that's hollowed out. So my plan of attack here will be my circle minus the triangle. And I happen to see that that triangle is a special right triangle. It's a 30, 60, 90 triangle. So I can see that the diameter of my circle, right, it's also the hypotenuse of that triangle, that diameter is 12. So a radius would then have to be 6. All right, so if I look at the 30, 60, 90, right, I know that opposite the 30 is the x, opposite the 60 is the x root 3, opposite the 90 is the 2x, and that's 12. So that means then that right here the x would be 6, and the x root 3 would be 6 root 3. Okay, so I have everything I need now to work the problem. So circle is pi r squared, and my radius is 6. So pi times 6 squared, we get 36 pi for the entire circle. Okay, triangle, right, it's a right triangle. I can use 1/2 base times height. My legs are 6 and 6 root 3. So I'm going to take half of 6 times 6 root 3. Half of 6 is 3 times the other 6, and I have 18 root 3. So now my circle, 36 pi, take away 18 root 3. They're not like terms. They do not simplify. So 36 pi minus 18 root 3, and then my units are squared. All right, next up, in part C, it looks like I have 3 semicircles. So they're all half a circle. Each of these is half of a circle. What are we given? Let's see. We're given that AR is 12. So right here is 12. Okay. And then ST right here is half of TA. Okay, we don't know TA yet, but we also know that TA is 2/3 of AR. Well, I know AR is 12. So if I think, well, what's 2/3 of 12? Let's say I solve that down here. What's 2/3 of 12? Right, I can always reduce top down or on the diagonals. So the 3 and 12 can go 1/4. Well, it's 8. So 2/3 of 12 is 8. So TA is 8. So then if I plug the 8 here and I take half of 8, well, this part here then would be 4. So I have all of my diameters, 4, 8, and 12. So all of my radii then must be half. So I have a 2, 2, a 4, 4, and a 6, 6. All right, so remember that each of these is a semicircle. Each one is half of a circle. So I'm doing what is half of pi times 2 squared. Add that to half of pi times 4 squared, and add that to half of pi times 6 squared. Right? Pi r squared is area. I want half of it for my semicircles. So I'm taking half of 4 pi, and add that to half of 16 pi, and then add that to half of 36 pi. All right, so now I have 2 pi, 8 pi, and 18 pi. So 10 pi plus 18 pi, I get 28 pi. So the area of the shaded region would be 28 pi. Units are squared. All right, for D, I put a little star here. This one can be a little challenging because we've got a lot of fractions, and there's a couple ways we could do it. So here are some thoughts. I could build off of my circle. I could remove the hexagon, regular hexagon, and then I could take 3/6 or 1/2 of what's left over. That would be fine. That's one way to do it. But we also learned about sectors, right? We learned about sectors, okay? And we learned about segments. And I have here 3 segments. Let me draw in some pathways so you can see that clearly. So let me go like this and this. Okay, let me straighten this guy out here. Okay, so I see my sectors now, my slices of pie, and now I can see more clearly that these are 3 segments. I'm going to do it this way, but again, there are multiple ways you could do it. 3 segments. Okay, so to get to each segment, I'm really looking at a sector minus triangle. So I'm going to calculate 1, and then I'm going to multiply by 3. All right, so I know that my diameter here is 18, so my radius is 9. All right, so let's keep that in mind. So my sector, I know that each of these angles is 60. Remember that a regular hexagon splits into 6 congruent equilateral triangles. So the central angles here, 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 all 60 degrees. So I'm looking at the ratio of sector to circle, 60 to 360, and then multiply by area of the circle, pi times 9 squared. So I want 1/6 of 81 pi. Okay, if I reduce that down, that would be 27 pi over 3. Okay, so that's my sector. I'm kind of done there, right? There's nothing else I can do to simplify that. And then the triangle, let me draw it out. I know it's equilateral, and I know that right here is 9. Okay, I'm going to split it right down the middle. Splits into 2 30, 60, 90s. So right here would be 60, 30, 30, 60. So here, if I have a side that's 9, these are both half. This is going to be 9/2 and 9/2. Okay, so what gets tricky about this problem is just the fractions. All right, so then the height, I take that 9/2 and I multiply by √3. So 9√3 over 2. Okay, so area, right, is 1/2 base times height. So half of 9 times 9√3 over 2. So if I'm multiplying fractions, it's easiest to view everything as a fraction. So I'll put that 9 over 1. And if I multiply what's on top, I have 81√3 over 4. Okay, so now I know the area of one segment, 27 pi over 3, and then take away 81√3 over 4. But remember, I have 3 of them. I have here, here, and here. So I need to triple. Oh, and I think I wrote this one wrong. Let me fix that. That should be 27/2, not thirds. Let me fix that. Let me show you why. So 81 and 6, right? If I divide them by 3, right, that's where I get 81 divided by 3 is 27, 6 divided by 3 is 2. So I caught that right there. That should be a 2. Okay, so now I have 3 of them, so I need to triple. So let me multiply by 3. So I have to distribute then that 3, and then what's going to happen? Right, it's like 3 over 1. So on top I have 81 pi over 2. Okay, and then over here I have 3 times 81, and I get 243 √3 over 4. All right, then that would be units r squared. All right, so a couple of ways I could have gotten to my overall area here, meant to be a little bit of a challenge problem. So put a little star next to it, and I'll put a star next to the one that is pretty similar on your homework as well. So I'll make that optional in your homework. It's a little bit trickier, but a really good challenge problem. All right, looking at E. All right, so E, I see that I start with a regular hexagon and I've portioned off a part of it that looks like this triangle right here. So what do I know about that triangle? Well, I know it's isosceles because all of my sides are the same. So let's start there, right? I can recognize that as isosceles, and I'm just going to rotate it so I can see it a little bit more clearly. So it's an isosceles triangle. I'm going to rotate it like this and draw it out like that. And I know that this whole part is 24. All right, so what else do I know about it? What do I know about the angles? What do I know about this angle right there, the vertex angle? Well, I know that this is a regular hexagon, so if I want to get to the sum of all the angles, I can do n minus 2 times 180, and then all those interior angles are the same, so I can split it n ways. So if I plug in 6, 6 minus 2 is 4, 4 times 180 is 720, so if I take 720 and I split it 6 ways, well, each of those angles is 120, so I have 120 right here. Okay, so this angle right here is 120. Well, what happens when I split it down the middle and make those two right triangles? That 120 splits, so I see a 60 and 60, 30 and 30. Ooh, fancy, right? Makes a 30, 60, 90 triangle here and here. Okay, so now that 24 splits into 12 and 12. And if I want the height right here, right, my x root 3 side is 12. What is my x? Right, that shortcut that you've heard me say many times is I need to take a third of the 12, that's 4, now multiply by root 3, 4 root 3. Okay, so I have everything I need. It's just a triangle. I want to do 1/2 base times height. So 1/2 of 24, and my height is the 4 root 3. So half of 24 is 12 times 4, and I get 48. And then root 3 units are squared. Okay, one more. So here in F, right, looks like I'm starting with this regular hexagon, but we've connected opposing vertices, and we end up with really just two equilateral triangles, right? That's really what I need to solve for. So I could picture this as like a third of the regular hexagon, or I can picture it as just two equilateral triangles, and that would be probably my approach to this problem. So two equilateral triangles. Okay, so let's look at each one. So here I can see that a radius is 3, but in an equilateral triangle here in the regular hexagon, these are equilateral triangles. So we know that a radius and a side, they're all the same, right? Here these are 3, and then here also. Okay, so let me look at it blown up, right? Let me solve for 1, and then I'll double. Okay, so here if I split it right down the middle, right now I know that this is 3, and I have my angles to fill in. So right here would be 60, and then 30, 30, and 60. So right here would be half of the 3, so I'll write that as 3/2 and 3/2. Okay, so my two short legs right opposite the 30 is 3/2. So then the height, if I multiply by root 3, I have 3 root 3 and then over 2. Okay, so I have my base, I have my height, I just see some fractions here. So area 1/2 base times height. So 1/2 of 3 times 3 root 3 over 2. Okay, again, it helps to see everything as a fraction. So I'm going to go over 1 like that. So 3 over 1. And then I can multiply all across the top. So I have 9 root 3 over 4. Okay, but I have 2 of those triangles, so I have to double. So if I double, now I have the 2 and the 4 that can reduce. Let me just put that over 1. So that 2 and the 4 here and here can go 1 and 2. So I'm going to end up with 9 root 3 over 2. All right, 9 root 3 over 2, and units are squared. All right, so like I said, it kind of gradually got harder with the shaded region. You just want to have a game plan. What's your plan of attack for getting to that shaded region? All right, have a good rest of your day.